Hello, this presentation is for the 16th International Conference on Advanced Engineering entitled A Semantic Model for Wise Systems Graph Matching Algorithm. More specifically, I will present the matching of two formalism. This presentation is presented by Abdelhafid Dahani, it's me, and supervised by Professors Ilham Alloui, Flavien Vernier, and Sébastien Monnet. The first thing I will present myself. I am Abdelhafid Dahani and PhD student in computer science in the third year, holding a master degree in application architecture and development engineering, and I worked as a software engineering with a lot of companies in Morocco, USA, and France. Before entering the main subject, I will put you on the context, and the context of this presentation is the wise object. We will present what are the wise objects and the conceptual view of a wise object. The first idea of wise object was to create an object that could learn by itself and about itself to moderate attention from the end users, respecting the calm technology presented in 1990 by Mark Weiser and John Seeley Brown. Currently, the object has the knowledge about its capabilities or its functionalities, the knowledge about its use, and he can analyze this knowledge and generate new one, also react according to its knowledge. To do so, a wise object respects hardly the MAPCA loop to monitor, analyze, plan, and execute an action. The conceptual view of a wise object is composed from two phases. The first one is when the wise object receives request. He is in the awake phase. During this phase, he can deliver a service or answer a request from the end users. And the second phase is the dream phase. He can do the introspection, learning, knowledge analysis, and the management of this knowledge. And as we are seeing here, we have no request during the dream phase. In contrary, we have a lot of requests during the awake phase. And what will be presented in this presentation is what's happening in the dream phase. In the dream phase, the wise object generates the knowledge graph called STG for state transition graph. And this graph represents the knowledge of the wise object, or more specifically, the behavior of a wise object. As we are seeing here, we have three states according to the attribute value. This graph has no meaning, as you are seeing here, except the method's name. Open, close. These methods are useless to understand this graph by humans. And the questions here is how the object will communicate with human using this STG, and what are the limits of such an object. Now I will present the problem in a diagram. Like we have here the existing knowledge already in the wise objects, and this knowledge represented as an STG, as we see here. And the question that raised is, where can we find the meaning of that information? That lead us to a semantic problem. Like we want to give meaning to that STG to be understandable by human in order to give a semantic to the wise objects. And the answer, after some literature, we found that the formalism called IOSTS contain the meaning of the behavior of a system. I will present it in more details in the next slides. All of this process is to give the ability to the object to communicate with human using a language that has a semantic, like a meaning for humans, not communicate with a numerical manner. And in the end of this presentation, we will see how we will link those two graphs to have an enhanced graph with meaning or with semantics. So we will see what does it mean an iOS test and why using an iOS test. As we see here in the title, iOS test for humans to machines communication. Firstly, why we are choosing this iOS test. iOS test stand for input-output state transition systems. And in Oracle or controller synthesis, the iOS test graph is used to model and to describe the behavior of such systems. And these graphs are those graphs are given by developers. So they are given by human, and that imply understandable by human and has the semantics. As a definition, it's just an automaton syntax that allow a finite description of infinite transition systems. As we illustrate in the figure 4, it's an iOS test representation of a roller shutter. And as we see here, we have two circles. We will call those circles localities. Here we talk about locality closed and here locality open. And those localities is defined by the value of height here. So when we have the value of height between 0 excluded and 100, so the roller shutter is open. And when we have the height equal 0, the roller shutter is closed, and those arrows are just the transition. Like when, for example, I execute up function and I have here a condition, I increment height and I switch to the open locality. This is more details, but the most important for us here is the localities closed and open. And I need to mention here that the locality closed and open, closed, it contains just one state of the system, is when the roller shutter is closed, height equal 0, but here it contains an infinite state represented in a finite manner in the iOS test. What comes next is how to use this formalism called iOS test to enhance the STG generated by the Weiser object with semantics in order to communicate clearly with humans. Here we have two formalism. The first one is the iOS test given by developer, and the second one is the STG generated by the Weiser object. And when I talk about attribute, I mean the variables in the STG. So I won't say this a variable, this is an attribute, as it is gotten from the entity. And level equal 0 here, it's the state, it's a state. Level equal 50, it's a state. Level equal 100, it's also a state. And on the other side, we have the iOS test, and the question here is how to extend the generated knowledge called STG with the conceptual knowledge given by the developer using a matching algorithm based on graph morphism. The first thing we need to know is we need to have a correct iOS test. And for now, for this algorithm, a correct iOS test is an iOS test that has not any duplicated locality represented in this formula. For all Q and Q prime in the set of localities, the domain of the variable height here is X. In this locality Q closed, intersect the domain of X height here in the locality Q prime in the locality open need to be an empty set. And as we see here, if we apply this formula on those localities, we will have an empty set. Before beginning the process of matching the state, for example, 0, 1, 2, with one of those localities, we need firstly to find an attribute here in the STG that match a variable here in the iOS-TS. And for this first version of this algorithm, we will suppose that we have just one attribute here that match one variable here, represented in this formula. So exists a unique variable in the set of variables, exists a unique attribute in the set of attributes, such as this variable is equivalent to this attribute. Here, I mean equivalent is represent the same thing. They represent the same information. So this sign equivalent is equivalent to the domain of attributes is included or equal to domain of the variables. We have here level equal as 0, 50, 100, and here height is between 0 and 100. So the domain of level is included in the domain of height. So we have this condition is correct for these two formalism. The last process of the algorithm is matching the states here with the localities here based on the domain of the attributes and variable. This process is represented in this formula and drawn by the algorithm using those magenta arrow. And we see here for all states here exists a unique locality here. We can't match, for example, a state with two localities. If we have a result like this, it means that there is an error at most in the iOS-TS, because we can't have an STG that is incorrect since it's generated by the Weiser object. And we are based on the value of this attribute need to be included in the domain of the height in some locality represented in this formula here. The value of the equivalent attribute in the state I need to be in the domain of the variable here height in the locality, for example, Q. If it's correct, that implies that the state VI is matched with the locality QG. To conclude, three phases for the algorithm. The first thing is the uniqueness of localities. The second thing is the variable matching. And the last thing is the state matching. And the algorithm will generate this enhanced graph with knowledge represented in the iOS-TS, or with semantics represented in the iOS-TS. The last thing is here the current future work. We are working now on many variables here, how to match an STG that has a lot of variables with an iOS-TS that has a lot of variables. And this is really a complex task, because we need to know which attribute match variables, and this is a tough process. Why? Because as we see here, we have level, for example, match height, since level is between 0 and 100, and orientation match angle, since orientation is between 0 and 90. Okay, this is the first matching, but there is a second one. If we see here that orientation is between 0 and 90, is also in the domain of height, and this is really a complex problem of decidability. And the algorithm will give us two matching. The first one is based on level, height, orientation, angle, and the second one is based on orientation and height. And we are working how to push the algorithm to near the human decisiveness, because for the machine, both results are correct, but for human, one is correct. Thank you.